The next presentation, I think, will be Andy King. And also about modular arithmetics.
I know, it's the theme, isn't it?
All right, here you go.
Thank you. Okay, so I'm going to talk about modular arithmetic, and the title of this paper is Polynomial Analysis of Modular Arithmetic, and the title is sort of carefully chosen to have a sort of doff the cap to an influential paper that was written by Marcus Müller-Ohm and Helmut Seidel on the analysis of modular arithmetic. And it's work that was done chiefly by two of my students, Tom Seed and Chris Coppins, with help with Neil Evans, who works applying verification to microcontrollers. Okay, so if you are of a particular persuasion, you can do a lot worse than entertain yourself by reading a book called Hacker's Delight. So Hacker's Delight is a compendium of fascinating and entertaining algorithms, and it is quite sobering because you can apply sort of textbook techniques to lots of these very simple algorithms, and lots of the methods that are so precious to us fall over in subtle ways. So this is a simple algorithm, and I've called it MI because it calculates a multiplicative inverse. So given an integer a, the function will return an integer x. And the crucial property is that if you multiply a by x, the result is 1 modulo 2 to the power of 32. Now what you have to do here is you have to interpret your signed integers as unsigned integers to make sense of that. Now I think what is fascinating is that conventional methods, and there are lots of these that reason about nonlinear systems, are inadequate here because we have an interaction between the integer and modular properties of the program and the nonlinear properties, and clearly the domains that just express modular properties in a linear setting are also not adequate to even deal with this simple program. Okay, so programs like this are not quite the motivation for the work, but I'll talk about some more motivation later. But I think that's an interesting motivation for the first part of the talk. So here I've got like a sort of unpotted history of, if you like, a timeline of work that's fed into our work. There was the Marcus Müller-Ohm paper from 2005. It was an ESOP paper and then a Toplas paper. And there was also a paper by Deepak Kapoor, and that's another influential paper that we're going to build on. And in that setting, the invariants were systems of polynomials where the coefficients were rationals, and Grosvenor-based techniques were used there to formulate, in particular, a join operation and a variable elimination operation. And we're going to take those operations off the shelf and use them in this setting without any more comment. Now, a particularly interesting paper here is a work that is a SAS paper in 2008 by Andrea Flexiter and Michael Petter, also with Helmut Seidel, and it was about the inferring systems of polynomials, again, the context of modular arithmetic. And I think this is a sort of very telling paper because it sort of indicates the delicacy of working in the modular setting. So let me comment on this, and I think this is another sort of sobering comment on how tricky this work can be. So in this particular paper, the force of the work is to build a system of weakest precondition transformers in the context of negative guards. So if we look at this sort of top line here, what we've got is a negative guard, and the way to read this is that P does not equal 0, that's the guard. And then we've got a condition expressed as a polynomial Q that we have to satisfy. And we want to infer another polynomial such that if that holds before the guard, then the guard filters out values such that the values satisfy Q. Now you can be forgiven for thinking because this is the way things work in a field setting, that the weakest precondition here is P and Q is the product. But when we work in a sort of modulo setting, we can have a sort of tricky problem here, because the precondition can vanish, it can reduce to true, and that can compromise the soundness of the approach. And this is a very subtle thing that can happen in the peculiar case of the modular setting. So, for example, if we set P to 2x, okay, and Q to 128x, then their coefficients, when we multiply them together, are 256. So if we work modulo 256, the product PQ vanishes to 0. And any assignment will actually satisfy that product. So if we choose the particular assignment x equals 1, that satisfies the polynomial 0, or 0 equals 0. So that passes the disequality, but actually violates Q. So I think that's really, really intriguing. But don't think that I'm sort of dissing this paper. I've got a lot of respect for this paper, because I think it points to important ways of taking our particular work forward. But it does indicate that how tricky it can be to work with negative guards in this particular setting. In our work, the main contribution is looking at negative guards and positive guards. Okay, so just to whet your appetite to some more, again for sort of entertainment, it's also sort of worth commenting on how rich the domain is in terms of expressing joins. Okay, and I think this is really quite intriguing. So we've got two systems here, P1 and P2, indicated in red and blue respectively. And if we look at the solutions to these systems, okay, we get 2 points, 2 red points and 2 blue points. Okay, and if we calculate the join as specified in the Deepak-Kapoor's paper, lifted to the setting of modular integers, we get a join that adds 2 further points. So it's quite an unexpected join, but I think what is interesting is we don't populate the whole space here as you might expect with values. So when you work with modulo integers, you get very rich joins. Okay, and it's also telling to see that the join here is expressed also as a system over 4 polynomials, and each polynomial there is no worse than cubic degree. Okay, so when you calculate the join, often you don't end up with these huge unwieldy systems. You end up with systems which are often the same size, but with a lot more expressiveness. So I think this is a very interesting and tantalizing domain to actually work with. Now, I think the most perhaps important part of this domain, and this was the motivation for the work, because we were interested in microcontrollers. Neil Evans was interested in reasoning about bit-level properties for the analysis of 8-bit microcontroller code. Okay, and I think the main value of this particular abstract domain is that it satisfies the ascending chain condition. Okay, and the force of this is that it allows us to calculate systematically best transformers for some completely wacky sequences of operations to get some very interesting abstractions, to give like a very tractable way of reasoning about sequences of bit-level operations. And here's a particular example. The first thing I want us to see is, first thing I want us to observe is that when we work in this setting, when we have systems of polynomial equations where our coefficients are modulo a power of 2, we end up with a finite domain. Now we can actually see that, okay, because if we just think about how many points we would have, let's think concretely to make this easy. Let's suppose our bit width, and henceforth we're going to call our bit width omega. So let's suppose our bit width is 3. Then how many points can we have? Well, Z8 has 8 points in it. Working over 3 variables, we can have 8 times 8 times 8, 512 points. So in a sort of the most concrete domain we can have would be 2 to the power of 512 points, which is, of course, finite. Okay, and we won't be able to represent all those points with systems of polynomials. So that means the numbers of systems we can have is also finite. Therefore, we must satisfy the ascending chain condition, and we can use that to compute best transformers. Here's one we computed earlier. So it's a best transformer for Z is equal to the bitwise and of X and Y, just over 3 bits to fit on a slide. And it's this monstrous and quite unexpected system of polynomials here. Now, how can we actually compute this? Well, this is not our work, but we sort of leverage off it. And I would go so far as to say that the particular domain really adds legs to this work of Tom Reps. It was an algorithm that appeared in VimKai, and it's a best transformer algorithm. Okay, and here I'll just give a synopsis of his algorithm so you can see how it fits into this setting. Okay, so let's suppose we've got a symbolic representation of a particular operation, and we call these things these days SMT formulae, right? Okay, and you can get like a whole load of low-level sequences of machine operations, transform them into SSA, and then encode that with an SMT formulae. We do that all the time. And then we've got this iterative algorithm here, which computes a best transformer for this relation. So how does it work? Well, we iteratively relax our system of polynomials P. So firstly, we set P to be an unsatisfiable system. That's a polynomial system which has just got one polynomial in it, 1, which is unsatisfiable. And then we've got a loop variable. Now, what's the key idea here? Well, what we do is we take our symbolic formula that we want to over-approximate, okay, and we take the best abstraction that was calculated thus far, which is P, and we encode P, and therefore its negation as an SMT formula, and encode that with phi. So when we present that to a SAT solver, what we're asking for is a solution of phi, which is not yet represented by our evolving abstraction P, okay? And if there is one, because we're using a complete solver, we get a set of bindings. We encode those bindings as a new polynomial Q, and then we relax P with Q to get a new system of polynomials, and we keep going in this fashion until we don't get a solution, and then we reach our fixed point. So that's a completely automated way of working, but it only works when your domain satisfies the ascending chain condition. And I think that's the real power of what we got here, because it plugs in with this method beautifully, and we found it to be useful in practice when we reason about microcontrollers. Okay, so let's talk about the domain a bit, and then I will then talk about some of the domain operations, in particular the sort of novel aspects of those domain operations. Now, what I'd like us to see as a take-home message is that the key operation that's used in many of our weakly relational domains, namely closure, carries over to this setting. So we've adopted that architecture here, and we've reduced lots of operations to closure, and the key computation problem is actually computing closure, and with that in place we build our whole edifice of domain operations, which we then plug into our abstract interpreter. Okay, so let's just think about what our concretization operation is first. So we're going to take P, and P is a system of polynomials. So let me just explain the notation here. So Zm x is the set of all polynomials over the variables x, where the modulo is m. Okay, that's the way to read that. Okay, and the interpretation of P is just as the set of vectors, right, such that when we evaluate a small p, a polynomial from big P, okay, that polynomial vanishes with the vector a. So we substitute, if you like, the value a1 for x1, a2 for x2, and so on and so forth. We evaluate p, and if the result is 0, then that p describes the tuple of integer values a. Okay, and this gives us our concretization operator. On top of that, we can build our closure operator, at least in a theoretical sense. Okay, so what's our closure operator here? We're going to take a set of polynomials and we're going to enrich it, okay? And taking our sort of lessons from octagons, we're going to throw in all the polynomials which are actually entailed by our system P. Now, what does that mean? Well, we take our system P, we concretize it, okay, to get all the solutions, and we build a set of P's, little p, I just should have used a different notation here, where the system P has a characteristic property that its solutions enclose that of the system big P, okay? So I bundle up all the P's, which are entailed by big P, and that's our closure. And now we're just defining things in a theoretical way. And the value of this is that then we're not burdened by the fact that we can rewrite our systems of polynomials in different ways. This gives us a canonical representation. It's an infinite representation. It's a massive system of polynomials, but at least we've got a canonical representation. Okay? And with that in place, we can build an abstract domain that turns out to be a finite lattice, and we enjoy the sort of properties that we really like. We've got a Galois insertion, and in particular, we're not lumbered with magicking up a widening. Okay, that's fine. Well, I hear what you're saying from the floor. You're thinking, well, this is fine, but all that guy's done is turned one difficult problem into another difficult problem. That's working with this massive set of polynomials. And I'm going to respond to that now. And what we're going to do is we're going to use bases, which are a finite representation of these otherwise infinite sets of polynomials that are closed systems. Okay, so what do we need here? Well, we need here the notion of an ideal, okay? So what's an ideal? Well, an ideal is a set of polynomials that's closed under addition. Okay, so we can take any two polynomials in our ideal, we add them together, and that's also in our ideal. We need that property. And the ideal must also have the property that if we take any polynomial in our ideal, and if we scale out that by any polynomial that's not necessarily in our ideal, that's also in our ideal. Okay, so that's what an ideal is. Now, the cool thing about our ideals is that we can represent them with small, compact, finite sets of polynomials, and we use the notion that we use the notion of a basis here. So if we've got a set of polynomials B, what we can do is we can generate, and that's what we mean by this. We generate an ideal from B by, guess what? Taking all the polynomial combinations, adding things together, and doing various scaling. This generates this uber big infinite system, but crucially, we're representing this ideal with a compact finite system B. Okay, so that's the tactic that we actually recover tractability. Okay. Right, okay, with that in mind, let's go back to the problem that we used to set up this talk. And it's I've got here the flow graph of MI. I'm going to just use this to sort of work out the operations we need to support, at least to reason about this particular program. Okay, so what have we got? We've got assignments to constants, assignments to variables, assignments to polynomials, not surprisingly, and we've got assumptions, which are both positive guards and negative guards. Okay, now, what we've done here is we've actually reduced the problem of verifying that AX equals 1 to a reachability property, okay? So if node 7 is not reachable, okay, then the only path is to node 6, which tells us that AX has to be equal to 1. So that's the way we've reduced this to a reachability problem. Okie dokie. So with that in mind, what we're going to do is we're going to try and build these operations at the top, okay, using algorithms at the bottom. I'm going to work up this lattice against the directions of the arrows to build things. I'm going to give you some insight as to how our architecture fits together. And I'm not going to talk about joining, I'm not going to talk about elimination, because we're just adapting previous work to our new setting. Okay, the thing at the bottom is a Grosvenor base. So let's talk about Grosvenor bases. People spend their whole career talking about Grosvenor bases, but I'm going to do it in 2 slides, so I apologize if I upset anyone here for my glib statements. Okay, so I think the simplest way to understand a Grosvenor base is to think about the notion of reducibility. Okay, so we can say that one polynomial is reducible by another. P is reducible by Q if we can eliminate the leading term of P by subtracting multiples of Q. Now, that is a comprehensible notion, I believe, and we can see that with an example. So let's suppose that P takes this form, it's 2x squared plus 3y, and Q takes this form, 2x plus y. We can see what the leading term of P is, that's 4x squared, right? And we can eliminate the leading term, 4x squared, by multiplying P in a particular fashion, i.e. by minus 2x, okay? Adding the multiple of Q to R, and in doing so, we eliminate the leading term, okay? So here we're doing a form of reduction, and this might feel Knuth-Bendix-like if you've been in those AI courses, okay? And that's because what we're doing here is we are like deriving a polynomial that is strictly smaller. We need this to actually get a determinating algorithm. Okay, so that's the idea of a reduction, and we can use that to stipulate what we mean by a Grosvenor base. There are lots of alternative definitions, but we're going to run with this. So we can say a basis B, a set of polynomials, is a Grosvenor basis, okay, if we take any non-zero polynomial in the ideal generated by B, okay, and P is reducible by one of the polynomials in the basis, a PI, okay? Now, what we can do, and it may seem surprising, is that we can take any system of polynomials, we can crunch them through an algorithm, and there are lots of algorithms that do this. Probably the most famous is Buchberger's algorithm, and that can produce for us a Grosvenor base. So a Grosvenor base is derivable from any system of polynomials. And this gives us some sort of wonderfully useful properties. I mean, one way to think about this is that a Grosvenor base is a bit like doing triangulation. It's like triangulation of a system, not a linear system, it's like triangulation on steroids, because it's working over polynomials. Okay, and once we've got a Grosvenor base, then we can check various properties. And you can see where they'd be useful from a sort of abstract interpretation perspective. What we can do is we can check to see if a polynomial, right, is contained within an ideal, and do that in a computable way, even though the ideal is an infinite object. We can check with one ideal is contained within the other. I mean, I know what you're thinking, oh, that'd give me like a fixed point check. That's dead good. And we can also eliminate variables from an ideal, and that's useful for projection and for variable assignment and things like that. And you can even do things like rationalize or revisit bit blasting using Grosvenor bases and compute, a much denser bit blasted version of a bit vector formula using Grosvenor bases. And we got a paper on that in SAT last year or the year before. So lots of useful things you can do with Grosvenor bases, and they fit surprisingly well in the sort of modular setting. Okay, so that's the background on Grosvenor bases. It's got a tick, we're moving forward, stay with me. Okay, so let's go up to covering now. So covering is like one of the key operations that we do. We really want to get to closure, because that gives us our stuff, but we decompose closure into an operation called covering, and covering here, is a bit like a partitioning operation. I'll explain that intuitively. You can go to the paper and you can see there is an algorithm for that, and it uses Grosvenor basis to do a form of forward checking, if you recognize that terminally from constraint solving. Okay, so here's an example. We've got F1, it's a system of two polynomials, right? Okay, and we can think about the solution set for F1, which is of course given to us by our gamma. We've seen that already, and it's this set of points here. Now, what's a covering for F1? Well, a covering for F1 is a set of tuples of polynomials that give us a parameterized representation of F1. Let's just see how that works. So the first thing to note is that we've got our points, our concretization of F1 here, and we've got a set of points here, A1, A2, and A3. And if you look carefully, you will see that if we union all the points in A1 and A2 and A3, they give us the concretization of F1. Let me just try and convince you with that informally. Okay, so let's scan the concretization right to left. We've got this point here. We can see that it's there. Then we get these 2 points here. We can see they're there. And then we've got that point there. We can see it's there. And I hope you get the idea. We've got all the points in the concretization, but no more. Right. Now, what I want us to observe now is that we can represent these points of A1 and A2 and A3 in a particular parameterized way. Okay, let's look at A3 first, because that's simplest. Okay, A3 is just 2 points, and we can represent those points as in terms of a parametric variable W1, which ranges over all the modulo variables between 0 and 15, okay? Okay, and if we were to plug these values into the second position of the second coordinate of this linear function, you can see that if we plug in 0 here, we get the value of 7, we get that one there. If we plug in the value of 1, we get the value of 15, and any other values, we also get 7 and 15 and so forth, okay? And the first polynomial here is a constant. Okay, and if you look at A1, that's a bit more elaborate. Here we've got 2 polynomials, both of which are functions of W1, and W1 ranges over all the integer variables. Okay, so the take-home message here is that a covering is a set of tuples of polynomials. Each polynomial is itself defined in terms of a parametric variable, but not necessarily one. Here's an example here where we've got a covering for this space, okay, and it's defined in terms of two parametric variables. Okay. Now, perhaps what's surprising is that we can actually compute this decomposition accurately and even efficiently. And we do that by virtue of the fact that we can use Grosvenor bases to work out how we can divide up our space. Okay, some more of that in the paper. Okay, so that's the intuition behind the notion of a cover. Right, but what we want to get to is the notion of a closure. Okay, we want to get a finite representation of all the entailed polynomials so that we can compute our join. Right, and for that we need a bit more stuff, I'm afraid. Thanks for your patience. What we need is something, the notion of a null polynomial. And we thought we'd found something new in terms of a null polynomial. A null polynomial, to use our terminology, is a polynomial that is vacuously satisfied. So here's a system of null polynomials, and you will see what I mean. Let's just look at this critter at the end, 8y squared plus 8y. Here the modulo is 16. And you can see that this polynomial is satisfied when y equals 0. The whole thing vanishes to 0. But also when y is 1, because we get this part becomes an 8, that part becomes an 8, modulo 16, that's 0. But also when this is a 2, right? And also when it's a 3, and so on and so forth. So these are polynomials which always hold, irrespective of the assignments on our variables. We call these null polynomials. And in fact, null polynomials arise in encryption. So people have studied these extensively. And there's even a way of systematically enumerating the null polynomials. And perhaps more surprising still, there's even a way of systematically calculating a Grosvenor basis for the null polynomials. Okay, and we're going to make use of that. That's a paper in the Journal of Symbolic Computation. Okay, so with that in place, we've got our null polynomials, we've got our covering, now we can compute the closure. Okay, so let's do it in terms of this example, f, and we can pick up the details in the paper. So we're going to calculate a cover for f, using the sort of techniques that I've pointed out on the previous few slides. And we can have a covering which breaks into three parts, where the first part is a tuple of polynomials. Okay, they're in terms of one variable, w2. Okay, we're going to generate the basis, n, for the null polynomials for a particular variable set, w2, and also for a particular modulo. Okay, and with that in mind, what we do is we're going to do a form of projection, which, if you like, morphs together our null polynomials, okay, using a relationship that we set up between our covering and each of the variables in our system, x and y. Okay, so just to give you an intuition of what's going on, this polynomial here is asserting that x is equal to this term. This polynomial here is asserting that y corresponds to this term. That's what these two polynomials mean. We add them to the system of null polynomials, and then what we do is we project out w2. So what I want us to observe at this state, we can do all these things because of the machinery that we got. And when we do that, we end up with a Grosvenor base which takes this particular form, and for reasons that are explained in the paper, it will infer for us those entailed equations that we're actually missing that are needed in our closure. We can do up the other things as well. We sort of join them together, and if we do the results, then what we do is we end up discovering these missing polynomials that we didn't have before in our system that contain just two polynomials. Okay, so the take-home message, is probably all that you can deal with at this point, is that if we got covering, and if we got null polynomials, and if we got variable elimination, we can use that to build a closure operator. Okay, which is what we need for our domain operations. So then we got our closure, and then on top of that we can build our various domain operations. Let's just talk about our assumptions, and then I'll sort of close up. Right, okay, so let's how do we deal with our assumes? Well, what we do is we got the system that we got described thus far as our state. It's a big system P. We add our P to it and then compute the closure. We've got all those components in place. But we can also deal with negative guards using a trick here, which I think is utterly devious, and I am proud of, it must be said. So what we can do is we're going to observe that if p does not equal 0 under some sort of variable assignment, it means that p must evaluate to a value which is non-zero. Okay? Now, because we're in a finite setting, it must mean that that non-zero value is integral. Okay? And there must be a least bit in that integral value which is 1, and there'll be all zeros to the left of it. Okay? So let's just suppose that that 1 bit is occurring at position k. Well, if it's occurring at position k, then what we can do is we can take that value and shift it by omega minus k bits. That will multiply it by 2 to the omega minus k. We'll end up with a value that's 1, 0, 0, 0, 0, 0, 0. Okay? And that value has to correspond to the value 2 to the omega minus 1. We don't know what k is, so we've got to consider all values of k. But using this argument, we can reduce a negative guard to a positive guard, which of course we can actually model. So that's cool. So you can see the scaffolding we've actually got going on in this stuff. We're building what we want on successively more and more complicated objects, and the algorithms are in the paper. Okay, so we got the bits, and I'm not talking about the other elements because they are more standard. Okay, so let me just finish up. So what have we got? We've got an abstract domain, the modular polynomial abstract domain, that satisfies the ascending chain condition. And that's just really good for calculating best transformers. I think that's the real value of this work. Okay? And we can use it to find invariants we didn't have before. But perhaps that's no surprise. We've introduced a closure operator for MPAD. And that's doable, and it's calculatable. We built it into a system, and it works. It needs a little bit of tuning, but in other words, you need to reflect on how Grosvenor bases are calculated, and we make comments on that on the paper. But you can get a reasonable system, and we can calculate invariants in this program. I think it's now up to 32 bits in less than a second, so that's okay. And we support positive and negative guards. And perhaps one interesting sort of unexpected take-home from this work is that in the paper we describe a way of reducing the complexity, the size complexity of polynomials using a reduction technique that seems to be new to computer algebra. So that's a nice feed from abstract interpretation to the world of computer algebra. And on that note, I will stop.
All right, we have time for some questions. All right.
Hi, so thanks for the super interesting talk. And I was curious to hear a little bit more about the covering, if you could give some intuition. The covering, if you could give some intuition of how you choose the pieces of your covering and how you are actually able to compute that.
Okay, so the intuition is that if we have a system of polynomials, okay, what we can do is we can just choose a particular bit in one of the variables, and we can assign that bit to either a 0 or a 1, and that partitions our system into two systems of polynomials which are disjunctive. Okay, that's it. We actually do that in an intelligent way so that we don't get lots of divisions. So we don't, in fact, what we do is we take our system of polynomials, we calculate a Grosvenor base, okay, that tells us a sort of good splitting point. So it's a bit like forward checking, okay? We sort of do a split and we apply this tactic recursively. Does that help?
Yeah, thanks.
Right, next question.
Yes, I was wondering if you had implemented this system and what is the, maybe the theoretical time complexity of the operation that you present, but also the practical complexity, for instance, on the example that you show, the motivating example.
Okay, well, I think I'm going to try and skirt that question, not because I'm being devious, but I think it's, in one sense, the wrong question to ask, okay? And what I mean by that is that we are here using a classical algorithm for calculating Grosvenor bases. And Grosvenor bases algorithms have it's well known they have double exponential complexity for solving particular problems. But it's a bit like SAT, right? So in SAT, what's happened is that we have rapidly evolved from the point we can only deal with 100 variables now the point we can deal with 100 million variables. And it's a bit like that with the sort of growing the base algorithms. So in the last decade, there's been incredible evolution of methods. And in our paper, we just talk about using sort of one classical technique, and it's called the Grosvenor-Muller rules. And the Grosvenor-Muller rules reduce the number of what's called S polynomials you calculate. Now, we sort of implemented this, and we had like a 4-bit problem. We were working on 4-bit problems initially, and our fixed point was taking over a day to reach a fixed point. We applied these rules, and it brought the running time down to less than a second. So, I don't think, and that is like a standard rule. So I don't think we can sort of underestimate the value of the techniques that are out there in the computer algebra literature. So I don't think it's helpful being obsessed with the complexity, because the complexity is horrendous. But because now these Grosvenor-based solvers are so powerful, and we can just think of them as being a bit like a sort of SAT solver. And it's worth noting as well is that we are just using like very old 1960s technology, which was specialised to the modular setting, which we've added the Grosvenor-Muller rules to, which we haven't written up yet because that is research that we haven't written up. But because that requires quite a lot of analytical proof work. But on top of that, there were these what's called F series of algorithms, like F2, F3, F4, and F5, and these are like super efficient algorithms. So they're orders of magnitude faster than Buchberger's algorithm. So what we should have done in hindsight is to start with them, right? But hey, we didn't know about them at the time. Is that okay?
Yeah, I understand that the theoretical complexity can be quite different from what happened in practice, but I was wondering if there were already some cases where you could apply your technique in practice. And
we could actually. So we could adopt a different representation of our polynomials. So there we can actually bound the degree that we're actually working in, and we could derive a complexity bound that way. I don't think that would necessarily be the best use of our research time, and the reason is that there is a method that we just hint at in the paper, where we can actually, which is like a runtime version of that, where we reduce the degree of our polynomials. So that seems to be a lot more sort of powerful method. Again, so I'm going to push back on that, because I think in computer science there is this thing that we've been obsessed by complexity, and that's actually stopped us doing things. And I think we're in real danger of sort of making that mistake in this setting.
Okay, makes sense.
Is that okay? There we go.
Right, then let's thank the speaker again.